talk about non-commutative lower bounds or an attempt to prove such a thing. I do not know how to prove it. I will start by giving some background, then some things that are known, and some nice mathematical questions that came up. So let's start by the model. So we want to compute polynomials. So I will use the same notation as before, but this thing is free non-commutative ring algebra. So we compute polynomials of the form x1 times x2 as before, but we maybe compute x2 times x1, and this thing is non-zero. It's another polynomial, and we want to compute things of this form. This is what we want to compute. And the model is the model of circuits. And the computation is, let's say, by circuits or formulas. This is exactly as before. There is some graph that defines the computation, and the vertices of the graph are either addition or multiplication. And except that at the product gate, we have to say who is left and who is right. And because this is the way multiplication is defined in this world. So if we switch the left and the right, then we switch the meaning of what is being computed. Okay? This does not appear in the community. So this is the model. And in this world, so let's say some examples of polynomials. And so there is again the permanent. It's permanent of an n by n matrix. But now there are many permanents. When we write this symbol, the product symbol, we actually need to say what is the order in which this multiplication is made. So there are many ways to define it. Here, let's take the usual, so let's do it column by column, or row by row, you can choose whatever you want. So there is this polynomial, and in this world it is non-commutatively VLP complete. So we know that the commutative permanent is complete for VNP. And the permanent is also complete for VNP in the non-commutative world. It's basically the same proof as variance proof. And so if you remember, VNP is the class of explicit polynomials. And Amir actually found it. And there is here the determinant polynomial. It's also in this form. And again, there are many determinants, possible determinants. And in the commutative world, the determinant is relatively easy. We can compute it using small circuits and small branching programs. But in the non-commutative world, this level of determinant is also complete. So Arvin, Kant, and then Chin, Prahlad, Alistair, and Shrikant wrote the same thing about the determinant problem. It's also hence non-commutatively NP complete. And they even proved more than this. They proved something stronger than this, some computational, more computational version. Not just formal polynomials meaning, but something more delicate. I will not discuss it. So these are some examples. So in some sense, the non-commutative world is different than the commutative. There is something that is easy commutative and we believe is hard non-commutative. And this is okay. So this is the model. And a few, very little is known about this model except one thing, basically. Noam Nissan, in a very nice paper, found a way to analyze these polynomials in a clever but simple way. Maybe I will say a little bit about it. So he showed, for example, that formulas for determinant, permanent, and I write it and then explain. Now this I'm not sure how you but it exists, PL must be exponentially large. So he proved a lower bound for formulas or even branching programs. So formulas, branching programs that compute the determinant and determinant that we define, that we know. And also another polynomial that I call palindrome. All of them can't be computed by small formulas, very large formulas. And the nice thing about this palindrome polynomial is that it can be computed by small circuits. I will not define it, but this shows a very strong separation between circuits and formulas in this model. And all of these use a very simple measure of complexity, which is just the rank of some matrix. So this is basically what we know. We don't know more. Maybe I should mention that although this model of computation, is weaker in the sense that it assumes less about the input it gets. So when the computation is not allowed to do such cancellations, the computation will work in a more general framework. For example, when the inputs are matrices, the computation can do matrix operation and still at the end it is guaranteed to work. So this is maybe one reason to consider this. Another reason is that because the computation is weaker, it assumes less on its input, it's easier to prove lower bounds. So proving such a lower bound is easier than proving for formulas and ABPs in the commutative world, and indeed we don't know how to do this in the commutative world. Okay. So this is what we know so far, and what I will explain now is some approach to prove a lower bound for circuits and to try to separate the non-commutative VP from VNP, the algebraic non-commutative version of the P versus NP question. And so the approach, I think it was a different one. So a lower bound approach. So as we have seen in all the lower bounds so far, this approach will have two parts. The first part is structural. We will find some structure that we want to use in the second step. So we will find some structure and use it to prove a lower bound. And we have some structure we can find, but we have no idea how to use it. And we is this result is together with Pavel Rubesh and Avi Wilderson. And I think so. The actual proof of this is not so interesting. Maybe I will say a little bit about it later. It is similar to what Mirek showed in the depth reduction, but here the computation is much less intuitive, so things need to be handled more carefully. But it's quite similar. But the conclusion from this structure, I think, is a nice conclusion. So so here is another question. So we call this question the sum of squares problem. And the sum of square problems is defined in a commutative world. So we want to reduce moving lower bounds in this very not structured world to something maybe simpler. So here is the problem. It's related to the toy question, toy example, what was the word that Mirek talked about. So the question is like this. Given some number n, what is the minimum k for which we can write the following equality? We write this simple polynomial, and beside it write this simple polynomial, and we multiply them. And now we want to write this in the following way. We want to write it as a sum of squares. And each of these things, ZL, is a bilinear form. We have I write x as a vector of variables, y as a vector of variables, and we put some matrix between them. This is a bilinear form, and this matrix can have, you can think about it. So this is a matrix, let's say over C, over R, over integers. You can put whatever you want in the matrix, and it gives another question. Or you can put finite fields there, it will give a different question. These will be the cases interesting for me, that are interesting for me. So this is the question. Like, you want to write this simple polynomial in this simple way. How efficiently can you do it? What is the least k that you need here? And so this is the question. And is the question clear? And so the theorem that follows this structural statement is that over the complex numbers, if you can show that k is a little bit more than linear, n to the 1.1, then non-commutatively VP is not VNP. So then in this world there is a polynomial that is explicit but is difficult to compute by circuits, for example the permanent. So we reduced some question about circuits, which is a general object, to something that looks quite simple to solve, but we don't know how to solve it.
So what should be a complete problem for VP? Non-commutative VP?
For VP, so in many cases, complete problems always arise because there is a generic circuit or a generic. But these things are not very, you can write what it is, it's not very informative. Every circuit can be transformed to some standard circuit. And this standard circuit, you just remove all the constants, it will become some complete polynomial. However, there is, I don't know, like a nice complete polynomials for this class. Do someone know the nice?
If you the left hand side the polynomial of something other than product of some square, some explicit polynomial, the conclusion is to go.
Yes, so yeah, so it's a. So I will add a comment. Any explicit f on right hand side, on left hand side, is good enough. So we can replace this polynomial, this is an explicit polynomial, it's pretty simple, by any polynomial that is explicit, and if we can show that this k is large, then the same conclusion holds. And the meaning of explicit, here to describe a polynomial, how many bits we need roughly log n bits, because this is an integer between 1 and n. So if we can in time polylogarithmic decide the coefficient of a polynomial, by this I mean explicit. Yes. So maybe I will come to this also later. Okay, so now I want to talk a little bit. Yes.
N will still remain the number of variables, or what's in this explicit?
Yeah, explicit I mean, let's say here we write always the polynomial of the degree 2 in x and the degree 2 in y, and there are exactly 2 n variables. Let's say this is the so now I want to talk about this question, this mathematical question, and I want to give some examples that you know, and maybe some examples that you don't know. So this problem, this sum of square problem. So let's start with the simplest case. What happens for n equal 1? Then we just want to compute x1 squared times y1 squared. And then how large can k be? How small can k be? then k is just 1, right? It's like x1 squared, x1 times x times y squared, right? This is very simple. And I remind you, this is in the commutative world. In the non-commutative world, this is not an equality. But we are now in the commutative world. So this is very simple. This is just commutativity, basically. For n equal 2, and what will be k, it's again 2, and I will write the formula just to show that everybody knows it. So this is the norm of a two-dimensional vector. This is another norm of the norm squared of a two-dimensional vector. And you can write it in this way. You can write it in this way. Maybe this is good. And right, you open up these things, there are 4 summons. Here you open up these things, there are 6 summons, but 2 of them cancel because they have the same sign. And what is this equality? This is a two-dimensional real vector is a complex number. So this is the norm of a complex number. This is another norm of a complex number. And this is the norm of the product of the complex numbers. Okay? So this is something that we know from complex numbers, that the norm is multiplicative. And it also holds as formal polynomials. The next example is n equal to 4, so it's 1, 2, then it's 4. Then it turns out that for n equal to 4, k is also equal to 4. So here k was equal to 2, here k is equal to 1, here k is equal to 4. And this is because of the quaternions. So they are in somewhat a generalization of the complex numbers. And so now I wanted to do, this is, if I would have been doing a presentation, this would be a picture of Hamilton, and who spent a lot of time thinking about quaternions. And there is some bridge in Dublin, I think, where he crossed, and in the middle of crossing the bridge, he thought about the quaternions, and he found it so remarkable that he put a plate on the bridge saying something, here I thought of the quaternions. And then he actually dedicated a large part of his life to this thing, and he wrote hundreds of pages about this. He was had a huge contribution to physics, and he thought that this will be, and he knew the importance of the complex numbers in physics, and he thought that this will be like very influential. And so for some time it was very well studied, but as time progressed, I think now it is not as well known maybe as in Dublin's university, in Hamilton's university. So for n equal to 4, k is also equal to 4. And for n equal to 8, it turns out that also k can be 8. And this is something that is called the octonions. And this was discovered by Graves, who was somehow a student of, he was in New Hamilton, he talked about it. So he found a 8-dimensional version of the complex numbers. And something that is interesting about it is that another property is that the complex numbers are a field. The quaternions are almost a field, except that you lose commutativity. It's no longer commutative. The octonions are not commutative, but also not associative. You also lose associativity when you go to 8 dimensions. So you lost commutativity, you lost associativity. What is there to lose anymore? So people thought about this for some time, and then at some point Hurwitz showed that there is really nothing you can lose. So he showed that if k is equal to n, then n is either 1, 2, 4, and 8. So these are the only cases where you can have equality in this. And so this is some history about this problem, and I recall the basic thing we want to show is that k can't be linear in n, and this shows that k cannot be n exactly. It must be at least n plus 1. So this is already some progress. So I want to tell you some things that we know about this k. So what bounds do we have on this k? So it will be asymptotic bounds. So k should be more than n. This is what Hurwitz proved. And k is trivially at most n squared, because we can open the brackets and we get n squared terms. But we know slightly more. We know that k, this is at least 2n asymptotically, or at least infinitely often it is 2n. And this is due to topology. And it's a real proof in algebraic topology of James, who actually proved something more than just this thing. I will not go into this. And it turns out that you can basically always save on this n squared also. So you can save a factor of log n. So there is some non-trivial computation that you can do. And this thing is the matrices AL. So to achieve this k, we need to find some matrices, to write some explicit matrices. And these matrices have entries that are integers and are actually, how do we do this? 1 and minus 1. So the matrices that do something non-trivial uses cancellations in some way, use cancellations. And this is also related to something that is called Clifford algebra. And somehow the construction of these matrices correspond to a construction of a Clifford algebra, or some matrix representation of a Clifford algebra. And so these are the bounds over R. So this is over R. Let's say. Except that here, except that this upper bound is already over Z, so we thought to ourselves, maybe over Z you can do something better. So over Z, you can first show that for n equals 16, you cannot have 16. This we know by Hurwitz theorem. But you can actually show that k is equal to 32. You already jump by a factor of 2, and this was proved by, I think it's Yao, it's not. And they have some group, mu also is involved in this.
So you know that k is exactly, that's the best possible, 32.
Yes, this is the answer. This is the best possible one. Over the real numbers for 16, so it's still open. It's somewhere between 29 and 31. I don't know, something like this. So this was what was known about over, if you try to use only integer matrices. And over Z, what we have shown, and I will explain it later, is that this k is at least n to the 6 over 5. So there is some constant there. So over integers, you can prove something non-trivial. It cannot be linear. Where?
But for the arithmetic lower bounds, you need it over the complex numbers? Or?
So, for the to prove something in the arithmetic, in the circuit world, the complex numbers maybe are not very important. What is more important is to have to prove something about circuits. We need to add a square root of -1. Okay, this is the point here. So if you can do all of this over the Gaussian integers, this ring, then you can already deduce something for circuits. And okay, so what will happen? What is my plan? My plan is to basically discuss the integer case and show you how to prove this upper bound and how to prove this lower bound. And we will do this by playing a game. It's quite similar to Sudoku in some way, or to some other board game, something you do in a newspaper. So, it's called intercolored matrices. So this is just a game. The name intercolored I did not give. This is someone else best to me. So now I will tell you what is this game and tell you how it is related to this lower bound and this upper bound. But first, I just define the game. So the game is like this. We have an n by n board. Chessboard. No colors on the edge. And we want to write plus minus I in cells. So in every cell we are allowed to write plus or minus I. I is some number such that we have to satisfy some constraints.
I is an integer.
Yeah, I will be, say, an integer or some symbol. It's not so important. Such that first, the whole thing is a Latin square. So every row has distinct colors. So colors is what happens if I ignore the sign. I can be either plus or minus, but always it has color I. And the same thing is about column. Every column has distinct colors. So when we look at it, it's similar to a Latin square, but perhaps there are more colors than just n. And the last condition is where the signs come to play. So maybe I will write it here.
Any integer?
Yeah, anything. For now. Later we'll see how it is related. But for now it's just anything.
So, but there are like two colors, right? What do you mean the color again?
Color is, so maybe I will give an example after so here is, I'll start with an example. And I will, so an example is 1, 2, 2 minus 1. This is the simplest example. And the third property is that every 2 by 2 sub board, so we can choose any 2 columns we want, any 2 rows we want. We get a 2 by 2 board, but it's a combinatorial rectangle. It's not a consecutive rectangle. So it's either like what I wrote here, 1, 1, 2, and minus 2. So if one diagonal 2 colors appear together, then on the opposite diagonal the 2 colors appear together with opposite signs. Okay, so overall there is the parity of all the signs is 1 in such a rectangle. Or this is one option, or you can just write 4 different colors. This is also good. Okay, so these are the constraints. Every 2 by 2 subboard is either this or this. So if this is an example, I will give more examples. Or one more example. So I start by doing the same example, but then I add some new set of colors. And now I will add some columns. So if I write here a 3, so I want to add more rows. So if I write here a 3, then this one must be a -1 because this 3 and this 3. And we also have this thing must be a -2. Okay, because of this 3 and this 3. It says that this 2 is -2 here. Now, this tells us that this -2 and this 2, if this is a 4, this must be a 4 as well. Okay, so this is how we play the game. And okay, so this is an example. Maybe I will finish it. if I write here a 3, this becomes a -4. And now we have a 4 on the diagonal, so this tells us everything. So this -4 and this -4, 2 -2, and this -2 and this -2 -1, and this is a 1. And it should be that everything is now okay, although I didn't check it. I believe it. So this thing turns out to be the complex numbers. Okay, a two-dimensional thing with two colors is the complex number. This is a four-dimensional thing with 4 colors. This is the quaternions in a very different language. So I'm just, I didn't say how it goes, but I'm just giving you the analogy. And in general, so here is the observation. The minimal K such that we can color the board with colors from 1 to up to K is exactly the sum of square problem over the integers. So it's exactly the same problem. This problem is equivalent to the problem over the integers. And I will not show why this is correct, because it's not very interesting. You just look at it by yourself. Michael did a service to us all. You should do it in the privacy of your own home. But this is very simple. And now all we need to do to prove an outer bound, we should find something non-trivial, some non-trivial way to color it. We can always color with n squared different colors, and everything will be okay.
So, I mean, I guess why is it really? I mean, it seems like the plus and minus 1 seems like you're only using. It seems like the number of colors corresponds to the variables somehow. Like, I guess it's not clear to me why it's integral coefficients is plus and minus 1.
So a reason integral coefficients are equivalent is that if you square a real number, it's positive. This is the basic reason, and then you need to use it in some algebraic way. But the basic observation that if you square something, basically you cannot cancel squares somehow.
So when you say complex numbers, there mean only the Gaussian integers or all complex numbers?
If you, what is the analog for complex numbers? It's more, then it's not as clean. And then you have, in every position of the board, you will put a vector, a complex vector, and there are some conditions on the vectors. This is the analog in complex numbers.
You said 1, 2, 2 minus 1. That sort of thing corresponds to complex numbers?
Yeah, it encodes the matrix that tells you how to multiply two complex numbers. This thing. So, right, or some version, right? Complex numbers can be represented as something like this, right? There's two.
So the algebra over.
Yes.
B.
Yes. So this matrix, its square is -1. If I'm not, or maybe I did something wrong.
So the characteristic matrices of the colors are the bilinear forms that we use.
The bilinear forms are you can think about every such a thing as a unit vector in coordinate that is written with a plus minus sign, and you take the layers of this. Now it's high. It has k things. Each layer is a matrix.
So it's not the characteristic vectors of the column. It's not the same thing.
Of the columns of what?
Of the colors.
Colors.
Of the colors. Yes, colors. So
The sign characteristic.
yeah, it has columns. Yes. Okay, so now we forget about the non-commutative world. We forget about the sum square problem. We just have this game. Okay? And we want to understand how many colors do we need. So let's first try to do a non-trivial coloring. So here already, this is a non-trivial coloring. Instead of 4 colors, we use 2 colors. Here, instead of 16 colors, we use 4 colors. But if you try to repeat this procedure, Horowitz told us you will get stuck. This will not work. But here is a way to continue that will always work. So the first part is the upper bound. Using few colors. And we will not start with coloring an n by n tree. We will start by coloring a log n by n board, and the number of colors we shall use is n instead of n times log n. This will be the same. So coloring this with log n colors. With n, so this gives you some gain. So let's see how to do it. I will just do it 2 times and you will get the point. So we start with 1 and 2. This is exactly n and log n. And now what I will do, I will just add 3 and 4. And let's write 3 and 4 also here below 1 and 2. And now after we did this, what happened? We know what should be written here. Right, this is -1 and this is -2. Now we are in a position of n equal to 4 and log n equal to 2. Okay, we increased the size by 2 and added 1 column. We do it again. We take all of this, use completely new colors. So it's 5, 6, 7, 8, and this is 7, 8, and -5, -6. So I just took what we had so far, moved it, duplicated everything. So 1 became 5, 2 became 6. And now we want to add 1 more row. So we start by doing the same thing, 5, 6, 7, 8. I just copied this here. And now we know what should be the other thing. So 5 and 5 gives you a -1. 6 and 6 gives you a -2, -3, and -4. Okay, so we got now 8 columns, 3 rows, as we need. We have n colors. And what happens? Every square in this part, we know by induction that it's okay. Like if we just look on this part. Now, every square that touches here and here is also okay because the colors are distinct. And this is also true for everything that touches here and here. And the last thing to observe is the thing that touches, say, 1 and -1, by the way we constructed it, it will have 5 and 5 here. Okay, so you need, if you want to prove it by induction, you need to check some things, but this is basically the idea. So we got something by playing this game, and this gives you a way to write this equality of polynomials with some cancellations, this simple game.
And Maybe don't you have a -1, -1, 7, 7?
It seems that there is a -1, -177. Yes, so maybe you should write a -4 here. So Amir said that there here a 7 and 7, here a -1 and -1, and this violates the rules of the game, so I lost. But so I probably missed some sign in the previous step. But if yeah, so if there is one mistake, there are probably many mistakes. Yes. So I will not find the correct thing now, but this is the basic idea. You double it and add more each row at every step. And if you encode what is written here in the algebraic world, you get some non-trivial calculation going on. Some cancellations happen, and this game helps to see how to do it in a clearer way.
And now you just repeat it in overlogging times?
Yeah, and to cover an n by n, you take this thing and repeat it n over log n times, and you get what you get. So this is the other bound. This is an algorithm. Now I want to prove. So to color an n by n grid, n by n board, you take the n by n board and partition it. This is log n. To layers of height log n. In each one of these you use n colors. And you use n different colors in every layer. So overall we get n times n over log n colors. There are n layers, each one uses n over log n layers, each one uses n colors. The second part will be to prove how come you can't do it with n colors. What goes wrong? And I want to mention that for 2, 4, 8, we can do it with n colors. So there is something nice going on. Like in the beginning it's okay, then it becomes too messy to be so that everything is okay. And there are many examples of this phenomenon in perfect graphs, where you have some small collection of good, perfect things, and then things cannot be perfect anymore. So, I remind you what we want to prove is that k, the number of colors, should be larger than n, asymptotically. And the basic idea that if there are, so the idea, few colors imply that there is a local obstruction. So if the board has not many colors in it, we find some place in the board where things are violated. Okay? This I call a local obstruction. And this is similar. We will see that there is a problem in combinatorics called the Zarankiewicz problem that tells you that if there is a graph with many edges, there are some things in it. You can find structure inside it. So we will see an analog of this here. So the way to prove it is using two lemmas. We have two lemmas. The first is a lemma about the game. So the lemma tells us that if we have such a position in the board. Okay, I didn't write things that doesn't matter. It has 6 rows, 6 columns, and there is 1 on the diagonal and 2 and 3 here and 2 and 3 here. Then if there is 4 here, this is just another here. Then the lemma says that here there should be a -4. Okay, if you try to complete this board using this information, the only thing you can write here is -4. Okay, this just believe me, you can play this later if you want. So this is lemma 1. This is the lemma about the game. The rules of the game tell you this phenomenon. The second lemma is, I will like this. If there are few colors, then we can find, I will write it like this, 1, 1, 1, 1, 1. This is a 9 by 9 matrix. And in this 9 by 9 matrix, here it's 2, 3, here it's 2, 3, and here it's 2, 3. Where, of course, 1, 2, and 3 are just some names of colors, not necessarily 1, 2, 3. So this is the second lemma. If there are few colors, specifically if the colors is less than 100, then you can find this thing inside the board. Okay, these are the 2 lemmas. First, a lemma about the game. Second, a lemma of the Zarankiewicz sort. If there are few colors, there is some structure. And now, how does these 2 things give you a contradiction? So let's see, or how does the 2 lemma prove the theorem? So the lemmas imply the theorem in a very, very simple way. So if k is smaller than n to the 6 over 5, then we find this thing. And this is the second lemma. Inside the board, we found some subboard with this structure. Now, this, let's say here it's a 4. Then what does this must be? It must be a -4. And what does this must be? If we look on this and this must be again a -4. But now this and this violate the lemma. Okay, so here, this is the violation. So if there are few colors, we find some violation. Is it clear? Okay. And so to finish this proof, I just need to tell you how to do this. And this, I guess, you basically know by yourself if you ever solved the Zarankiewicz problem. But I will show you. It's a nice. Yes, I ignore constants everywhere. You can have it too. It's not really 100, it's like 1 over 10. So now we just need to prove this. So we do this in 2 steps. First, we want to find the color that appear many times, to have it on the diagonal. So, part A is left 1, the color giving M, which is n squared over K. there are n squared positions, there are k colors, there is a color that appears this many times. Okay? So this will be this color on the diagonal. And now we look on the matrix, the submatrix, which is n by n, that has all ones on the diagonal. If there is a minus sign, you can cancel it if you want. So we found this pretty large matrix. If k is not n squared, it's a large matrix.
Sorry, what did you say about minus signs?
Like maybe in the game there is a minus sign here. So then I multiply all of the row by minus and it's the same game.
Or we could take half of it.
Yeah, or you can take 1/2. So we found this thing inside, and now we want to find somewhere here a 2, 3, 2, 3, and a 2, 3. This is what we want to find. This is basically the structure, and after rearranging rows and columns, we get this structure. Okay. So now we want to say if there are few colors, then there is such a position. So the statement is, the observation of the claim, if k is smaller than some constant n to the 3/2, then we find such 2 and 3 times. Okay? So if k is not much larger than B standard, we find somewhere 3 times 2 and 3. Is it clear, the lemma? So this is exactly the Zarankiewicz problem, but let's prove it. It's a simple proof. So the idea is to write the n rows. This is n rows, 1, 2, to n on the left. So I'm now defining a graph, a parallel graph. And to write the colors, 1, 2, up to k on the right. And we connect a row to a color if the color appears in the row. So one has one in it, this and this. So we define this graph. We connect a row to the colors that appear in it. Now, what is the degree here on the left? How many colors appear in a row? This is n, basically n. Okay? So in every row, m. So in every row, there are basically n colors. This is because it's a Latin square, or a generalization of a Latin square.
You want a minus 1?
Yeah, so I ignore the constants. And now, what does it mean that there is no such triple? This means that there are no 2 rows, so that there are no 3 rows that are connected to 2 colors. No such subgraph.
I think that's why Amir did on the ones, I think, on the right side.
Ah, yes. Yeah. So we made it 2 to n.
No, on the right hand side.
On the one.
Yeah.
This, and this is actually n. This is also yes. So if there is no such triple of 2, 3, 2, 3 of 2, 3, this means that in this graph there is no 3 rows in which the same 2 colors appear. Okay, it's exactly the same statement. And this is called no k 3, 2. The complete graph with 3 vertices on one side and 2 vertices on the other side. And how do we, so the claim is that if there are many edges, how many edges are there? There are m squared edges here. If there are many edges, there is, and the number of vertices on the right is small, then there is such a thing. So we assume that, so this is assume, that there is no such trigger. This means that there is no such thing in the graph. Okay. Now comes the proof of the Zarankiewicz problem. How do you prove it? You basically count, so let's call this side A and this side B, okay, just for convenience. Vertices here I will call small a, vertices here I will call small a. So if we sum over all B, and we take the degree of this vertex, and we choose 3 vertices in it. Okay? So this is some number. This is the degree of the vertex B on the right. How many vertices on the left it is connected to. What is this number? This is the sum over B. The number of things like this B is connected to. Okay, this is exactly this number. And what is this number? Now we use the assumption. There are no every such triple to how many vertices, every triple on the left, to how many vertices on the right it's connected to at most 1. So this number is at most m choose 3. Every triple on the left is connected to at most 1 vertex. So there can be more than this. So this is roughly m to the power of 3. Okay, I ignore constants. Okay. So this is one side. The other side is just to lower bound this. So how do you do this? First you say, I ignore constants. This is roughly this number again to the power of 3. You can do it more delicately if you want. But let's do this too. Now the function x goes x to the power of 3 is convex for positive, for non-negative x's. So what is this? I want to now lower bound this. So I will write it like this. I will write it first like this so it will be clearer. There are k colors. I wrote it like this so that this will be an average of something to the power of 3. So this is at least k times sum over b, 1 over k db to the power of 3. This is the convexity of this function to the power of 3. So this thing is at least this thing. And what is this thing? This is 1 over k to the power of 2, because this is 3 and this is 1. And what is the sum over all degrees? It's just the number of edges. What is the number of edges? Basically m to the power of 2. There are m squared edges in this graph. Okay, so we got some inequality between k and m. What? 3. So m to the power of 6. Yes. So it's m squared here, and this is to the power of 3. So if you move things around, you get that k is at least. And so this is m6, m to the 3, it's m to the 3, and k squared, it's taking square root. So we get exactly this statement. If k is small, there is such a thing. We prove that if there is no such a thing, that k must be large. And this is it. We found such a thing, we rearrange it, and we find a contradiction. And so this is what happens over the integers. Over real numbers, there are many things to think about. Over complex numbers, it's even more complicated. And there I have no suggestion.
But this upper bound and lower bound is also not tight, right? So
So I don't have a conjecture what is the right number. I mean, maybe you can show that it doesn't fluctuate too much, but even this I'm not like it fluctuates this number from time to time. So I don't know what is the correct answer.
What about the rationals?
Rationals and reals are basically the same, as far as I know. No, it is the same because the completion of the rationals is the reals, and it's the same question. What else? On the other hand, I think it's basically the same question. But I don't know if this is the right way to prove lower bounds to non-commutative sequence. It's a way, and I think it gives nice questions that we can try to solve. I tried it. Yes.
Did you show the reduction from test solution to a solution to the P? Or a solution to the sum of squares?
Over the integers? No, I didn't. It's simple. And so I think I thank you now for your attention.
One last question about the field choice. So you said the theorem you stated from the paper with Pavel and Amir. So that requires you to have this lower bound of the complex numbers just because of the square root of -1.
Yes, every field is.
So if we had a finite field that had a square root of -1, then it would work as well.
Yes.
Okay, let's stand. We'll be meeting back here at 11:30.